Dancing in the Dark, a comparative analysis of orbital rendezvous methods in Orbiter Spaceflight Simulator and KSP. This is a physics category science experiment. Orbital rendezvous is the intricate process of bringing two orbiting spacecraft together in space. For example, how does one guide an 80-ton orbiter to meet up with a 420-ton International Space Station traveling at nearly 17,500 miles per hour at an altitude of 300 kilometers above the surface? First, we need to understand what an orbit is and understand orbital maneuvering. An orbit is an elliptical path around a massive body formed due to gravity. An orbiter goes forward so fast that it misses the ground entirely while falling. You can see this with Newton's cannon thought experiment, where a cannonball is fired so fast that essentially misses the entire Earth and is being pulled by gravity and travels in this curved trajectory, also known as an ellipse. Orbital motion is counterintuitive, however. When you fire your rocket engines, when you fire an impulse, it has two effects in an orbit. It has an instantaneous effect, where the velocity vector changes, and an overall delayed effect, which is caused by a change in energy state, which also changes your actual orbit. In other words, if you speed up, you'll start slowing down and ascending, and if you slow down, you'll start speeding up and descending. We can take a closer look at this with this orbital diagram here. We have a parking orbit here, and at perigee, the closest point in the orbit to the Earth, we conduct a prograde, or a direction of motion burn. Because of this, the kinetic energy of the vehicle increases, and inertia essentially carries you forward. And it overcomes gravity, so you start ascending at the same time. And while you're ascending, your kinetic energy becomes exchanged for gravitational potential energy. When you reach apogee, your kinetic energy is the lowest, and your gravitational potential energy is the highest. You can see this in the energy charts. And when you conduct a retrograde burn, that is opposite in the direction of motion, your orbit lowers because gravity overcomes inertia. You start slowing down, and as you move forward and downward, the gravitational potential energy is exchanged for kinetic energy. This means that the local orbital velocity decreases with altitude, and the period of the orbit increases with altitude. We can use this to our advantage and set up orbits and intersections such that we can achieve our orbital rendezvous. Spaceflight simulators like Kerbal Space Program, KSP, and Orbitersim offer an educational sandbox environment for experimentation and research with orbital mechanics without the constraints of real-life missions or abstraction of mathematical models. So I set up an experiment where a space shuttle must rendezvous with the ISS with these orbital parameters from this parking orbit. And I wondered what trajectory would yield the most efficient rendezvous. My hypothesis was that the Hohmann transfer would be the most efficient since it only consists of two thruster firings in the direction of motion, prograde, respectively. We tested this in Orbiter 2016, a spaceflight simulator. My three trajectories were the Hohmann transfer, my tangential facing transfer, and the step transfer, which consists of two Hohmann transfers or more. My dependent variables I was measuring was the change in velocity, delta V expenditure, the mission elapsed time, the closing velocity at rendezvous relative to the ISS, and the average phasing rate, which is the angle decrease relative to the chaser and the target. My results from 3 repeated trials was that the Hohmann transfer required the lowest delta V and number of burns, but it produced extremely high closing velocities. The step transfer resulted in the lowest closing velocity but required more change in velocity than the Hohmann transfer because it was more than 2 burns. The tangential phasing transfer was a nice trade-off between the various variables. My hypothesis was rejected, and the step Hohmann transfer resulted in the most efficient rendezvous with regards to delta V. However, it took 3 days of mission elapsed time to accomplish, which is quite realistic. It produced an extremely low closing velocity, however. Conclusion? My conclusion is that real-life space exploration missions are extremely complicated and constrained, but the fundamental principles do not change. The simulator experiment provided precise results even with assumptions of circular orbits, two-body gravitation, and impulsive burns. This testing is similar to the work of mission planners at NASA and Roscosmos. And here are my credits. Thank you.